All right, everyone, welcome to Paradigm Drift. I am so excited to be doing Paradigm Drift live for the very first time. So this is an improvement over the previous Paradigm Drift, which we did just with 4 of our friends in a room. Now we have a bunch of our friends here with us. We have a live audience. We have 19 theorists that have signed up to present. I know, it's very impressive. So before we get started, I figured we would do a little bit of, frame setting. I'm going to tell you what Paradigm Drift is like. I'm going to introduce our panel and associate musician, and then we will get to our first regular. So Paradigm Drift is the show where we give people the opportunity to present the ideas that they have about the world. A lot of what we do on the podcast is focused on the idea that it does not matter the background of the theorist in question. All that matters is that you have an interesting idea and you can put it into a concise form and send it out into the world. And so the letters after your name, where you come from, who you studied with, do not matter here. The only thing that matters is that you have an excellent idea and you can explain it to other people. To that end, you will have exactly 60 seconds after stepping up to the microphone to give us the most condensed possible version of your vision of the world. This is a challenge, I understand. I would encourage all theorists to start with stating the problem that they're solving, and I would encourage you to avoid getting too deep into the weeds too fast. Make sure we follow you. At the end, should we vote on who has the best theory?
Well, hold on for a second. Sorry, I don't have a mic. And if you go over 60 seconds, you're going to hear this sound. And that's the end. And we will turn off your mic if you keep going. So
this is true.
After that, we will interview you very briefly and find out who you are, where you came from, and why you started thinking about this, stuff like that.
Exactly. Let's see. Are there any other details that I need to include?
Oh, by the way, the name of the band tonight is the Baryonic Acoustic Oscillations.
Oh, well done. All right. We shall just present then, unless there's overwhelming arguments in favor of hierarchical ratings. I don't know how we feel about this.
I think the goal is not really to necessarily pick the best, but to help people get better at presenting their own ideas. Right? Everybody's got a little something, and we're going to try to help them get better at bringing it out.
So to help us in this endeavor, we have a dear friend, Patrick Van Reyes, who has been instrumental in putting this conference together. Would you like to say a few words, Patrick?
Yeah, so apparently I will be the innocent hand, I guess. I've never been an innocent hand before, so I find this a very... a very big honor and trust, I guess. I have no idea actually how this will go. This is the first time for me. I have seen a little bit from a previous episode, which seemed challenging for the panel members. So I'll do my best. But yes, I think we will try to be as constructive as we can.
And then playing with us, we have Chris Lehto, which I always want to say Lehto, but it's Lehto. Who of the Lehto files, and also turns out an absolutely spectacular banjo player.
It's questionable.
The standard is set. So our first regular of the evening is Dr. C.S. Unnikrishnan, who humbly asked if he could give us theory that is not a cosmological theory. So I'm very much looking forward to this. And Patrick, would you like to pick our first contestant of the evening? We will not look. Who you got?
Robin Booth.
All right, so Robin, so we can skip the so wait over there on the side, and then that way we can turn around quickly.
welcome to the stage, Uni. 60 seconds on the clock.
You got it.
We'll count you in on 3. 1, 2, 3. Hit it.
Okay. I have formulated a new theory of quantum mechanics which solves all the foundational problems without exception in one sweep. Its first part is to show rigorously that Schrodinger equation pertains to it is same as the continuity equation. So the equation and its wave function pertains to the ensemble. This solves the problem of collapse measurement problem. The second part is to separate dynamics and particle. It is not the particle which has a wave property, it's the dynamics of the particle which has a wave property. Then I write a modified Hamilton equation for the exponential of the action, and it solves the problem of two-particle correlations without non-locality. The details are in the archives. It is 1812.06088. Thank you.
Hey!
All right.
There we go.
Dr. Unnikrishnan, you have to stay for a few moments. We have some questions.
Yes.
So where should we open the stage? I didn't totally understand.
That was a hard one to follow. Yeah. It was more like an advertisement for a theory than a theory.
No, I'm saying there are two things. The Schrodinger equation is shown to be same as the continuity equation for probability, which is an ensemble equation. Therefore, its wave function pertains to the ensemble. This, as Einstein already advocated several times, solves problem of collapse, problem of quantum measurement problem. Then the single particle interference and two particle correlations, you need a new theory. It doesn't exist. It needs a new theory. That is a modified Hamilton equation for the action, which is a familiar quantity. So without adding anything new, I have solved all foundational issues of quantum mechanics. The details are in the paper, 1812.
Oh, we got to read the paper.
88. Explicit calculations.
Well, I mean, I suppose that the theory that is presented is that quantum mechanics is solved in the broad strokes, in the most broad strokes version of the story. Is that fair? That you have solved quantum mechanics?
Yeah, you asked me about any foundational issues in quantum mechanics. I will give you an answer which is satisfactory. No more mysteries, no more weirdness, no more superstitions like non-locality.
Why do things collapse in the direction that they do? Why do things collapse in the direction that they do? What chooses the collapse?
Yeah, but once it is an ensemble equation, there is no collapse. I can explain to you, but what I'm saying, I guarantee on money. I guarantee to give answer. No. I will show you with a calculation. It is a proof. It is not words. I will explicitly demonstrate solutions for every foundational issues in quantum mechanics we have ever faced.
So I think that this means that next time we have to have a working group on solving quantum mechanics. I bet you that we can collect a room full of theories that have resolved it finally. I love that Matt is off in the corner too, ready to drag the board out so we can start in on the equations.
I don't think we have time for that
I don't
today.
think we have time. Uni, thank you so much for kicking us off.
Okay, thank you.
I appreciate it very much. Patrick, do you want to pick our next name?
Ben Watson.
So Ben Watson's on deck, and Robin is ready.
All right, let's do it. We'll count you in on 3. So we have 1, 2, 3. Hit it.
Well, we see increasing evidence from JWST and other sources that we inhabit a static, i.e. non-expanding universe, as opposed to the expanding universe predicted by lambda CDM. And that model is supported by certain theoretical considerations. The problem with a static universe is we need to explain the cosmological redshift, which is explained by the Hubble expansion in the standard model. My solution to that problem is a mechanism that I've termed the genes contraction, named after the person who first suggested it. And it's based on the concept that atomic matter is in fact shrinking. And so the redshift we observe in distant galaxies emitted by atoms millions of years ago, where those atoms were considerably larger than the atoms we use today to measure that light. So hence we get a redshift that's proportional to distance. The precise mechanism for that I'm proposing is basically the shrinkage of atomic matter is due to its own gravitational field, and it inhabits its own Schwarzschild metric. And if you do the equations, the differential equations from that, you end up with atomic matter shrinking over time. And from those calculations, you can calculate the Hubble parameter, not only today, but projecting it back in time. And then you can use that to calculate your redshift age of universe relationship, and it ends up...
All right, so shrinking
Plenty of room for
atoms.
questions there.
Exactly.
So atoms collapsing under their own weight over the history of the universe.
Exactly, yes. So, you do the calculation based on the well-established length contraction that is inherent in the Schwarzschild metric, and you discover that something of the mass of a proton actually causes the proton itself to shrink minimally, like 10 to the minus 40 each time you insert it into that gravitational field. And if you multiply that up by the frequency of the proton or the hydrogen atom, you end up with this contraction, which exactly or near enough equals the Hubble rate.
Patrick, what do you think?
I think we need a name for this theory. So,
I've called it, being modest, I've called it after the person who first proposed it, which is Jeans. James Jeans,
Yeah.
the same Jeans who had the concept of the Jeans mass, which causes galaxies to form. So he was the one who first suggested it. I've got his actual words on my poster over there.
But let's say we want to kind of connect it to tired light theories or so. Is it?
It's a complete antithesis of tired light.
So tired mass, tired space,
Tired atoms.
tired atoms. Yeah.
Call it what you will. I'm going to call it the Jeans contraction.
So for me, it's interesting that the expansion of the universe is at this weekend, at the very least, and perhaps elsewhere, is considered to be sort of an extraordinary mechanism that it requires extraordinary proof. But yet you're more comfortable with the entire universe of atoms shrinking. Like, how big were they to start with?
They were big enough that when stacked together, they filled the whole universe. But it's in a sense a meaningless question. I mean, I believe the universe started off with 10 to the 78 atoms, and they were all stacked up one beside the other. But
So do you imagine like a bubble bath of just these like gigantic balloonia atoms that are just floating around? Like, do you have a picture of it in your head?
If I went back further, it would be pure speculation. So I leave that to the imagination. But yeah.
By the way, dude, where are you from?
I'm from the UK. I was until recently studying at Sussex University. I'm now a freelance. Whatever.
Are you an academic by your background?
No, I was in IT, apart from little excursions into trying to learn more about things during master's degrees and research degrees.
So if we're getting pinned down by PowerPoint, you can help us later?
Yes.
Try to talk right into the microphone for us.
Sorry?
The man has a name for his theorem. He started by naming it. Let's leave him alone.
Do you guys suggest new names for your friends' children as well?
She's always struck me as more of a Sabrina than a Sally, you know?
All right, I think we can keep it moving along.
All right,
That
let's
was
keep
awesome.
it moving. Thank you so much.
All right.
Gareth.
Gareth's on deck to his great dismay.
We'll count you in on 3.
I'm here because
Hold on. We're going to count you in. There's a formality to this.
Okay.
You ready? Because we got to get the timer started at the same time. 1, 2, 3, hit it.
I'm here because the problems of mainstream physics are very familiar to me, even though I'm not a physicist. I've spent the last 50 years thinking about music. There we also have an institutional academia which studies the details of music, but is incapable of delivering the real thing. Real experimentation and progress existed in what is now called the classical tradition, but is now only possible outside the academy. We live in a society geared to a war economy, which directly contradicts the needs of our species being enshrined in the morality of the great religions. The morbid nature of Big Bang cosmology, something pointed out by Shiloh, is no accident. It is the same death sentence which academia has passed on creativity. Free discussion of science by the unpaid is the way forward, just as music can no longer be assessed by its institutional or commercial endorsement. Free improvisation is a necessity.
Well done.
Hell yeah.
I'm not 100% sure that was a theory.
What's a theory,
A
Anastasia?
theory is
Explains facts.
Patrick.
Well, do you ever wonder why the classical music, the music written by people in academia, doesn't connect with you? My theory is an explanation of why this is the case. Why musical creativity has been made by people from the outside institutional knowledge. And I think it's very parallel with what you experience in physics. So that's a theory. What I mean is that the ideas being spoken about here can apply to philosophy, music, and all kinds of fields of endeavor. And I admire what you're doing because you brought the dialectic back into science, which is people discussing with each other on an equal level and not having somebody just shutting you up because they have letters after their name. And it just, my experience of music has been so similar, I wanted to point that out. So is it a theory? Well, it's a contribution to understanding what you're doing and saying it should extend itself beyond science to politics, philosophy, all sorts of other fields.
Just to be clear, it was not a criticism. It was merely an observation. I thought it was very beautifully written.
Okay, thank
I
you.
thought it was very beautifully written.
Yeah, Ben, don't let yourself be bullied by Nastya. I would say I can really understand it's a theory. It's just not a scientific one. It's a philosophical one.
But
and
I think science is based on philosophy.
Voila, and there we come to the demarcation problem. We don't know what science is.
Yeah.
So I think you're no less a member of this group than anyone else here.
Oh, thank you very much.
Where are you from, by the way?
I'm from London, but I spent 20 years in Leeds.
And what were you doing in the music world over there?
I was a journalist for a magazine called Wire magazine, which still exists, and I tried to be a rock journalist. I never got my foot in the door there, but with the jazz revival of the 80s, suddenly I could write about music, which gave me no money, but some status. Musicians want to talk to you because they need their photograph in magazines.
Do you play music also?
I've begun. I think of myself as a non-musician, but I give problems to musicians. I have a group of musicians. I think people should learn music by playing it, but if you do, surround yourself by people who really can play, and then you give them problems, and I find the resulting music a bit more interesting than very skilled people just comforting each other.
Mm-hmm. I love it. I love it.
Okay.
Yeah, it is interesting. I think it's really sad when I meet musicians who have never played conversational music. Like, they've never like jammed with anybody. Especially, I've met some really depressed people at conservatories who learn all of these notes, and they're very good, but it seems heartbreaking.
Well, a big inspiration for me is Derek Bailey, the guitar player, born in 1930. He died 20 years ago. And he pioneered what's called free improvisation. And a poet pointed out, he's not playing jazz. He's not copying someone else's voice. Actually, his rhythms are English blank verse, that he's speaking with his instrument. And we can all speak, and we all have our local rhythms. And I love jazz, but I don't like listening to people who are skilled at repeating jazz.
I feel you.
But if we come out of how we speak and play music how we speak, we all have special rhythms and a unique approach. One of the things that's wrong with the Eurovision Song Contest, for example, is that people don't sing in their native tongue. And so everybody's doing this kind of bad version of English, and it's very boring. Whereas, if you had a Romanian band followed by a Portuguese band, the music would be unique and so much better.
I love it.
Yeah, I think that it is really well said, and I think that it is really important. Where Shiloh's describing something very real, that you meet people who play instruments, and they're like, well, I don't really know what to do without notes on a page. And you always meet people that do the same thing with science. They're like, you can't say that. Like, I remember I had one of my friends studied philosophy, and I was trying to explain to her actually something very akin to Chris's theory of this like fractal nature of the universe. And she was like, did somebody publish that? And I was like, no, it's just like a thing I've been thinking about. And she's like, I don't think you can do that.
Yeah. I mean, I think your efforts with DemystifySci has communicated with me, because I came out of listening to records and YouTube. I can tune into a YouTube and see someone speaking and make my judgment on the basis of, do I like their voice? Do I like how they're presenting themselves? Which is something in music that you learn. You hear a saxophone and you decide, do you like it? And voices, singers, can you trust them? Are they real or are they pretending? And we're very attuned to people's voices and being able to divine the sincerity and to see what we think. And YouTubes and science YouTubes have, for me, become the best part of YouTube, because I can see people talking, and you're bringing back what's traditionally called in philosophy dialectics to science. And I think that's very important.
Patrick, do you have any thoughts?
Well, I think science is all about creativity. And this is, I think, the common theme everywhere here in the conference.
Yeah.
Where does it come from? Is it a skill? Is it a talent? Is it... Some people are too...
Patrick between us, because I have to be at the mixer and Shiloh's playing guitar.
Nobody
And I'm like,
can
we're
hear
going to have to talk about things at some point.
trying to silence me.
Finish your thought, Patrick.
Yeah, that was my thought. Creativity is one of the most important things in science, yet we don't really
For
understand.
me, each time you listen to music, it's an experiment. You expose yourself to music. It affects your body quite without your morality or your politics. It affects your body, and the discipline of listening to music is to reflect on that and to be honest about your reaction. So for me, each musical experience that we have is an experiment, and it becomes a fact. If somebody likes some music, it's a fact. You can't argue with them. If they've enjoyed some music, that's a fact. But you can unpack that fact, and you can start talking about it, about your background, what you know about music, what you were expecting when you went to this music, and you can unpack it and learn about where people come from and how commercialism affects things and so on. And you can have a reflection on what music is, which becomes scientific.
I like that. Musical experiment.
Yeah.
I love that. I think we should keep moving, but Ben, that was wonderful and very, very beautifully written.
All right, so we'll count you in on 3. You good? 1, 2, 3, hit it.
Okay, well, this is not really a theory. It's more of a philosophical discussion, and that's really to do with the nature of light. I am a firm believer that we are misunderstanding many aspects of light, that the way quantum mechanics formalizes light abstracts away from what's actually happening. And I firmly believe that actually a wave nature for light is a more real way to understand what's going on. And it's not, in that sense, I still believe that it is like a photon. So it's more like a soliton in terms of its shape. But I think it's a better way of explaining things like Compton scattering, stimulated emissions, and even attenuation through things like polarization filters. And I think it also couples with the idea of when you look at light, light effectively interacts with an electron, primarily with an electron. And I think therefore an electron is some sort of exciter in that medium. It is, for a sense, you can call it like an antenna. It couples to the field, and therefore essentially what a photon is energy traveling across the medium, and the electron is the thing that is able to extract the energy into different forms. I also believe that our idea of what an electron is also the idea in quantum mechanics that you have an electron, a muon, and a tau, and that they are different particles. I actually believe that they are the same particle, but they're just in different vibrational modes. And that's where I'll cut it.
All right.
I love that. Okay, so the photon travels and the electron extracts.
Yeah. Well, the photon is not actually, it's just a wave that's traveling across the medium. It's not a thing. You only perceive it as a thing because at some point you have to interact, and that interaction extracts the energy from that field, essentially. And whether you call it an ether, whether you call it a field, that is semantics at this point, I think.
Vibration?
Sorry?
Vibration?
Yeah, so the electron would be an oscillator in that. Yeah, so you're talking about resonant frequencies that you're creating. So when you look at an atom, for example, the quantization of a photon is because the atom is a structure that couples the electron. So there are only certain modes that are allowed that work, and therefore you end up with a quantization of a photon. Not because you can't create a photon at any energy, but because the system that creates it is restricted because of the way the electrons are shaped around an atom.
So do you think the electron is a physical object?
I mean, is any matter a physical? And I mean, what is a physical object?
Well,
I mean,
physical object has a surface and it has inward extension from every tangent on
Does
it.
it have a surface?
A physical object does, yeah. Just definitionally. Let's just define physical object as something that is a surface-bound volume with inward extension.
Well, yeah, but that's you as a thing interacting with it, and you as a thing are made of things that contain that, and those things repel each other, and therefore you're not actually touching anything. The forces in the things that you are made of repel each other.
Well, let's just say...
Do me a favor and talk into the thing called the mic. You can take it out of the stand, but you do have to talk into the thing that's called the microphone.
Yeah, so let's just say like all words could be broken down into either relationships or objects, so bodies.
I know
right?
where you're going with this.
All right,
but my view, just to.
So is it a relationship? Is it a relation? Is it an activity, or is it an actor?
In essence, what you perceive as a thing is a small component of a big thing. It's just a different oscillation within that thing. You perceive it as something separate and different, but it's not.
But do you treat the electron as the outer surface of the atom?
No.
No. So is
not in that sense. No, because it's the fields that create what you perceive as the surface. The electron is not a thing. The electron is an oscillation in that, and it creates a field, and that's what you perceive as the boundary condition.
So it's a concerted pattern of activity.
Well, I suppose you could argue, in your view, it's the fields that create your boundaries.
I wouldn't say that.
Okay.
Well, I mean, just because fields are like a bunch of measurements, right, or vectors, right? So they're sort of a predicted activity.
All right, the force that it exerts on the other particles surrounding it, however that force is then carried. Whether that's a field or whether that's a different ether or whether that's... I know...
Carrying forces reminds me of Star Wars.
May the force be with you.
And so, how does this relate to, and I don't want to use any dirty words here, but a virtual photon?
There's no such thing as a virtual photon in my view. Like, that's the abstraction I'm trying to get away from. What's the point of a virtual? It's a mathematical sleight of hand. We don't quite know what to do with something.
It's like
we know
matter.
We know that it goes from one state to another, so Compton scattering. So we're going to create something in between that transfers the data. Well, where does the data go? How does it no. Basically.
Agreed.
Well, I mean, okay, so the virtual photon is really a little bit irritating because it's basically this like arbitrary force carrier that's been included in order to make things stick together, right?
It's a fudge.
It's a fudge. Okay, so let's say that there is no fudge. I listening to you and Shiloh go back and forth, and like it reminds me of, you know how you can take the 3 Pac-Men and you can point them at each other and you get a triangle, and then like the voids between the Pac-Man make it look like there's the illusion of the triangle between them, even though there's no lines.
Yeah.
And I feel like this is a fairly common illusion. And then you can argue, like, is there really a triangle there? Is there really an electron there? Because ultimately there's some framing from where that mixes with human perception and mixes with the environment that then forces us to have to ask the question of, like, what are we really seeing? What are we really touching? Is it an illusion? Is it something that is real? How do we parameterize it?
Okay, so there are a number of things to unpack there. I think in terms of where we're doing virtual photons, that's a mathematical trick. There's nothing real about it. We never see a virtual photon. It doesn't exist. Whereas an electron, you can absolutely treat it as a real thing. What I'm saying is it manifests. We see it as a real thing because it's just something which is part of a greater system. But that doesn't mean you can't treat it as an individual. I'm not saying that there are no such things as electrons and that you can't find an electron. No, that's not what I'm saying. Electrons are real things because the way that we interact with it makes it
well, they do something.
They do something. Yes.
They do something.
They effectively they're like antenna.
Or like an action, right? Because I mean, like if you think about it, like
I know where you're going with it. They
well, I mean, I'm just like I think that it's a legitimate. It's a legitimate frame on it, right? Because we were talking to Baron Das, and Baron Das makes this point. He's like, what is a measurement?
Yeah.
Right? And so if what we're talking about is not something that we can see, it's a thing that we can measure, and we measure by virtue of voltage.
You can't, like, you're using the word see, but honestly, we're back to the same problem. Like, what do you see? You see photons.
I see patterns.
Like, well, yeah, you do see patterns. But so
I hope you guys caught that one.
So really, in terms of the way we interact with the universe, we're restricted anyway. Like, we only ever see in photons.
Doesn't it keep you up at night, though, how much of this is about stuff that we can't actually see and we have to infer?
Isn't that the wonder of it? That it's like and honestly, I think part of what I think is missing in science is the philosophical side of it. It's too easy to go into mathematical. If we can find an equation that fits, fine. And I know, Alexander, you're all about making sure that it fits, and that's fine. But I think at some stage you do have to ask the why. Why fundamentally, and maybe that's just me, I've always been like this. I've always wanted to try and understand how things work. I would take things apart and never be able to put them back entirely the way they were. But the point was to try and understand why something did the thing the way that it did. And the same is true when we look at the universe. And one of the most important things that we interact with is light. Mm. And the thing that interacts with light is matter, and primarily electrons. So there is a duality between those two that is important to understand. I'm not saying that I'm right, but that's the way that I think about it.
I think that's fair. I love it. And I love the way that you think about these things. I think that your presence and your insights are invaluable.
I just also want to add, man, like I'm not trying to just give you a hard time. Like I think it is important to ask why, but I think that it's also important to be extremely excruciating with our language so that we don't confuse objects and concepts with one another.
But I also think that you can come from a different perspective and see it in an entirely different way. Like there's nothing wrong with saying that quantum mechanics can mathematically predict it. That gives it incredible power, right? Because it is able to predict things all the time, but it doesn't tell you the why. It just gives you the probabilities of this will happen.
Right.
And I want to know the why. That's fundamentally. And I think there are different ways that you can come at the why. Eventually, you hopefully end up at the same point.
Hell yeah.
Revenge.
Wait, revenge?
Can you just
Revenge on
can you just
me?
quantify what revenge is here?
Your voice is not going to show up on the podcast. I'm sure. So, all right, yeah. Let's move it along.
Yeah, let's move. Okay. So the video guys need a second to come in. So Chris, you're up next after this musical interlude. Thank you, Gareth.
The next one on the mic is Mike.
Mike McCulloch, you are on deck. And for right now, we have Chris Lehto. Shiley, you want to count him in?
Yeah. Here we go. 1, 2, 3. Hit it.
Okay, this is Heisenberg goes to the mountain and then keeps going, right? So why does the solar system look like an atom? I think we've all had these large questions. Mendeleev observed patterns others missed. So arranging elements by atomic weight revealed chemical periodicity that really predicted missing elements. So I'm proposing that we observe the same periodicity in scale, actually in cosmic structure. So nuclear size determines chemistry, carbon's geometry enables life, iron structure builds hemoglobin. So this principle, I argue, scales. So stellar core size can determine planetary systems. Galactic core size determines star formation. The observation that atoms concentrate 99.9% of the mass in the nuclei. You look at solar systems also concentrate 99.8% in the mass. So the hypothesis is if size and structure determine function at atomic scales, then they should determine function at all scales. So I'd argue to you or encourage you to look at the actual size scales of the universe and note if there's any coincidences. I found many coincidences. So that's it.
All right, nicely done. The fractal organization of everything in existence.
Yes, the fractal universe, if you will.
How did you start thinking about this?
Actually, it was when I was forced to go to school every day. And I just asked myself, as I'm in terrible classes, although I enjoyed physics class very much, why am I here, you know? And then as time went on, I came to the observation or hypothesis that we're actually in a larger entity, a larger organism. And so, yeah, when you look back in history, they used the microscope. So I really argued that they bent light to actually discover microscopic life. And if you look at every scale below us, you see life, right, on the EMF spectrum. You see scales of life. But when you get to the human, it stops. And so anthropocentric principle, we basically think we're the center of everything and we are the top organism, right, on this planet. And everything above us, we're confused. Why was I born into an organism or organization that I'll die in? Same way your cells were. So really, I came to that And then when AI came out, I used AI. I call it AI whispering, where it really kind of mind meld with it. And you can use the breadth of AI to say, what are the scales of the universe? And it can list out. And so I noticed that at 10 to the 3 log, it seems like there is a scalar pattern. So a cell is 1,000,000 times smaller than you, 10 to the 6, and a human is 1,000,000 times smaller than the planet, 10 to the 6, and the scale keeps going. A galaxy is 10 to the 6 times smaller than the observable universe. So, and that from Alexander Unzicker found other coincidences where large Dirac's large number hypothesis, 10 to the 42, where do these large coincidences come from? So it's basically an observational theory. Like Mendeleev looked at the atomic structure of elements and he found periodicities. So the argument is there a periodicity to the scales of dimensions?
I like that most kids go to school and get bored and doodle in the margins of their notebooks, and you come up with a fractal theory of nature.
So do you think that we can go even smaller and that the million keeps going on?
That would be the argument, right? Is that it just keeps going if everything is relative. And I've thought that as well. Like we can't see really a proton. You had pictures earlier, I believe, of what we understand what protons or atoms look like, and it's really just a sphere, right? So what I argue is, could that be like a dimensional blurriness, like when you look into a pool, because of the dimensional change in frequency of the light, it looks different. So
I always think of it, Nasti always points out airplane propellers, like when they're spinning, it's like a totally different experience interacting with a spinning airplane propeller than one that's just static.
Well, it's like event horizons. It seems as though our universe is bounded by event horizons at both ends of the scale, right? We can't see past a certain point.
Your voice will not appear on the podcast.
And so do you think that you can also use this theory? It's almost like a scientific theory that you can test. So if you have some weird thing happening at a larger scale, to find it at the smaller scale, and for example, if it's not there, then perhaps it's also not really there in the larger scale and we just imagined it. Like
exactly. I think the most powerful part of the theory is that it has predictive power, right? That was the whole point of the periodic table, is that they could say, oh, there should be an element here that has these properties. And so we should see certain relationships. If a solar system really is in a functional form but different scale as an atom, then we should be able to make certain predictions. If black holes, like there's stellar-sized black holes and then there's galactic-sized black holes. Why is that? Is there any equivalent in atomic nucleus or in atomic physics? Or can we learn from what we see in the cosmos?
I'm sorry, that was an accident. I'm so sorry. I'm so sorry. Sorry, the black hole thing just, yeah, sorry.
Yeah, well, that's what Mendeleev did, right? Is he saw, or he noted similarities in the atomic structure of things that gave us insight into things that are properties of matter at our scale. So
do you think that you've come across something that's a missing piece like that? Or that you've been able to see something as you put together these tables that reflects something that we haven't noticed yet? Or do you think that that's still in the future?
I think that I couldn't have done it without AI, the breadth of analysis that you can just get from artificial intelligence. And as it got better, then I was able to add on physics, because really when 4 came along, when ChatGPT 4 came, it was much better at physics. So then I could span across many physical laws and then ask it to find the coincidences. And so, and I think it did find many coincidences related to octaves, frequencies. I related it to music.
Where would you say you have spiral galaxies on the smaller scale?
I think my argument is that everything is connected. Gravity has no distance limit. So the argument is you have the same force or the same general rules, but we see different emergent properties depending on the scale. So you have the same force, but based on the scale of that dimension, you will see different physical properties. So that's the argument. Exactly. Yeah. So if you look at, I have a chart over there. If stars are similar to atomic nucleus, then we should be predicting that there are, binary systems. There's tri-systems, similar to atomic elements. Maybe there's stars with many elements, or.
If you look at young stars and as they're forming, they can form spirals that look identical to spiral galaxies.
Okay.
That will not appear on the podcast, but maybe we can repeat it.
Yeah, Gareth says that there's stars that can, when they're forming as baby stars, they can spin and appear in spiral shapes.
It's the clouds that condenses you can get. I can show you. I did a video on the fractal, actually finding the fractal nature of comparing galaxies and stars.
Excellent.
And there are some flat structures anyway. Saturn's rings.
Do you see this in plasmas? You're a plasma guy.
Like helical filaments, maybe?
Flat structures, maybe on surfaces, yeah.
All right, we have the endorsement of the plasma guy. We're cooking with gas now.
Excellent.
All right, let's. Thank you so much, Chris. That was excellent.
Thank you.
And give it.
All right, back to work.
And give it up for the Baryonic Acoustic Oscillators.
All right, we'll count you in on 3. Ready?
No. After Mike McCulloch, we have
Michael Gunning.
so Michael Gunning. Hopefully, you're in the room. You are on deck. Now I'm ready.
All right. 1, 2, 3. Hit it.
Okay, hello. So the problem I was trying to solve was the problem of inertial mass, that everybody's assumed that things keep going in a straight line until you stop them. But why is that? So to explain that, I could talk about a motorboat on a lake. If it accelerates in one direction, it'll see more waves in front of it than behind it. So it'll get a pushback against its acceleration. That's a bit like inertia. Well, I've managed to show that any object in the universe travels through the quantum vacuum, and it sees a similar effect. It gets pushed back against its motion, which explains inertial mass. But how about if the boat is accelerating very slowly on the lake, then the waves would be too long to exist on the lake. So then its inertial mass would disappear. Well, this also happens in nature at the edge of galaxies where stars accelerate very slowly. And I think they lose their inertial mass, less centrifugal force, and so that's why galaxies can rotate faster than expected without blowing up. And this theory also predicts things like Big G.
Yeah.
All right. That was very well done. Okay, so inertial mass disappears when the boat goes really slowly, simply because it's not, or when it accelerates slowly, because the wave in its bow wave is longer than the wavelength of the lake, you're saying?
That's right. It's bigger than a lake, so it can't exist. Because for a wave to exist on a lake, you must have nodes at the coasts. And if that's not possible, then the wave can't exist. It's not an exact analogy, I have to say, but...
I was going to ask, because the boat does still have inertial mass at that point.
Yes, that's right.
Okay.
It's an analogy, but not an exact one.
Do you think that at the edge of the universe there would be some distortion of inertial sensation if there was an edge to the universe? Let's assume there is. Would you feel more pull towards the center as a whole? Like, would one side of you be experiencing more inertia than the other side of you?
I think if you were at the edge, you'd be attracted to the horizon, the cosmic horizon, because fewer waves can exist close to the horizon because it's damped. They're damped by the horizon, so you get a pull towards any horizon you want. You see.
Can you talk? Can you grab the microphone actually and talk right into it? You can pull it out of its holder. Yeah, I think it'll be easier that way. Just stay in the box that Francisco made. Francisco's putting us all in the box. So. Oh, Patrick.
I just think I was watching a part of your podcast interview with Chilo and Anastasia, and I was like, okay, I have to watch this later because it's getting a bit too complicated here. And now, in just 1 minute, you explained it to me like I understand it. I think this metaphor or analogy is such a powerful tool. I think it's very well done.
Are these electromagnetic waves that we're talking about?
So the actual waves are waves in all fields. So it's an excited form of the quantum vacuum called Unruh radiation.
I remember now.
So, yeah.
I remember talking about this.
Okay, so, go ahead.
Well, it's a very powerful educational tool. I think we should emphasize this. This is one of the better ones that I've ever heard in my life, I think.
Whoa.
Maybe.
All right.
So effective.
So, what is can you explain Unruh radiation? I mean, you did explain this to us already. And I know that you will have a talk on this, but can
Patrick put it? Can Patrick restate the theory in a sentence or something? Yeah, I mean, you said it was one of the coolest things you heard. So
you really put him on the spot here, man.
I'm sorry, you don't have to do that. I'm not trying to.
I'm not so good with boats. They make me sick.
I want to have that experience that Patrick had.
Me too.
Shall I explain?
That would be fantastic, yeah.
Yeah, so there's a quantum vacuum everywhere, but if you have a horizon, if you insert a horizon into it, then if you get a particle pair formation on the horizon, one of the particles goes behind the horizon, and one of them comes forward out of it. Now, normally, these virtual particles will recombine very quickly, but if the horizon is there, it'll separate them. And so one of them will become free and real. And that's the origin of the Unruh radiation, which has now been seen, by the way. It's not just a theory.
And so the horizon in this case is just the limit of the sphere of influence on something that's elsewhere?
Yes, that's right. So a horizon is the limit to the world that the object can see, because information can only travel at the speed of light. So if an object is accelerating away from a part of space, it won't see things from within that space. So there'll be a horizon there.
Why do you need the particle pair? Because you said that you have this particle pair and one goes beyond the horizon and the other goes in the other direction.
Yeah, to conserve momentum, virtual particles are formed in pairs. So they have different charges, different orientations, and different directions.
Wasn't somebody was it Gareth? Somebody was just saying virtual particles are a mathematical backflip or trick of some sort. Can you respond to that?
Well, one of the predictions of this is a Casimir effect, but not everybody accepts that. Another one is Unruh radiation, which has now been directly seen by Lynch et al. A couple of years ago. So there is now direct evidence for the quantum vacuum in this form.
I'm going to change direction. How is the space thing going? You launched things into space.
That's right. So
I think you're the first person on this show to launch something into space.
Well,
Congratulations.
I didn't do it personally. It's just been launched to test.
Chris is like,
yeah, so it's up there. It's orbiting, but they haven't switched on the thruster yet.
And you're testing predictions of quantized inertia?
Yes, that's right. So they have a capacitor up there, and one of my predictions was that the capacitor will see thrust.
That's very cool. When are they supposed to switch on the instrument?
Yes. Yeah, I should say my prediction was that an asymmetric structure will see thrust, and somebody else suggested a capacitor would be a good way to do it.
When are they supposed to start the experiment? Do you know?
Well, it was supposed to be a few weeks ago, so everybody's just waiting to get the go-ahead.
Just building up tension as much as possible.
Yes, that's right. Yeah.
The satellite hasn't been feeling well.
Well, people note this is a spaceship. The analogy is just perfect.
Mm.
Do you get seasick in space? Space sick?
Space, yeah.
You're asking Patrick personally?
Yeah, I'm asking. Excellent. I will not be going to space then.
All right, well, that was awesome, man. I look forward to hearing more from you tomorrow. We'll hear more from Mike later.
Michael Gunning's coming up.
All right. You got the timer up?
We got the timer up, and who's on deck, Patrick?
I don't know what's happening, but I feel like I'm not so innocent. I was sitting next to this person yesterday, and he was asking to have more eyes on his theory. It's Howard Landman.
Universe delivers. All right, let's do it.
All right, here we go. On 3. 1, 2, 3. Hit it.
Standard model of particle physics is held up as one of the most successful theories in physics, but it is littered with dubious renormalized affinities, multiple fundamental particles, and nothing at all about gravity. For over 70 years, physics has failed to unify general relativity and quantum mechanics because, in my view, they are both only mathematical constructs and incorrect interpretations of reality and are thus incapable of unification. The standard model of particle physics is littered with inconsistencies and is nothing more than multiple layers of mathematically complex abstractions describing physically meaningless ideas, while general relativity cannot even derive a value for the gravitational constant. In this paper, I revived the idea of the ether and show that how the three main forces, that is, electromagnetic, strong nuclear force, and gravity, are all the result of a single simple process occurring within the electron. I propose that the structure of free space is a tetrahedral lattice of nodes, and I have reinterpreted mu naught as the density of free space and epsilon naught as the compressibility of free space. The length of the connecting rods between the nodes is a new fundamental constant, but with this very simple model, I can easily explain the nature of and derive values for all the constants of nature in the title of this paper. In explaining the origins of these fundamental constants, I have also explained the nature of inertial and gravitational mass and why the photon has no gravitational mass. This model also explains the mass and charge of the tau, kaon, pion, and muon particles and proposes an explanation for neutrinos. Finally, this model also proposes an explanation for dark energy, dark matter, and the matter-antimatter asymmetry.
Michael Gunning out here trying to game the system.
I feel like this presentation so much fits you because you can cram so much of information in just a little thing, and that's what your model is. It's so awesome. With very little tools, you have everything getting out of it. You tried a little bit the opposite with your presentation, but it's a really an awesome model. I recommend everyone to look at it. It's really, I'm a big fan.
Okay, have you a question for me?
I thought you were auctioning something off for a second there.
I don't know what your model is yet. Did you?
I heard something about interconnected nodes, which I perked up at.
There's a model.
I have a few toys here. I can explain it to you.
Oh, we got props.
We got
My
props.
goodness.
Okay. This is our first propped theorist.
Bring them back into the box.
The box.
Whoops, the box is entirely-
You have to stay in the box.
Yeah, you must
though.
stay in the box, though.
All right.
So I said in the introduction there that I believe that the ether is made up of a tetrahedral lattice, which is the same structure as the diamond crystal, which again is the replication of scales. So
Shiloh just leaned over and whispered, "Terrence Howard agrees."
So what I'm suggesting is that this unit here is one of the kind of the little cell units within the tetrahedral lattice, and this is what I think is a virtual electron. I know we had talked there a minute ago about what virtual photons were, but I think a virtual electron has the potential to become a real electron, and a virtual positron has the potential to become a real positron. So if you look at that little structure there, it has 4 axes of symmetry. Yours has the 4 on it as well, yeah. It has 4 axes of symmetry. And if you look at the little, what I call
the timer has gone off. You can talk slower.
I have to cram as much in as I can because I have a lot to talk about. So if you imagine this trigonal thing on the top rotating 120 degrees, and the one on the bottom rotates the opposite way 120 degrees, it'll compress this structure, and it'll oscillate continuously like that, because these little components are like springs under tension. So the whole lattice outside this is pushing in on this structure, and it'll continually vibrate and oscillate and moving from one axis of rotation to another continuously. And when it does that, it generates 3 different types of waves. And the first wave it'll generate is a transverse wave, which is kind of spherically symmetrical, and that becomes the electric charge of this particle. The second type of wave it generates is when this twists, it twists the whole lattice along the axis of rotation.
Can I interrupt you?
Yes,
What
you
is
can.
this the lattice of? This is like the lattice of the ether? This is
Yes,
the lattice...
the
Okay.
lattice of the
So
ether.
this
We
is like
can
the universe is filled with this
Yeah, you just
structure
imagine that thing
at the tiniest scale.
Yes.
And the deformations of it are the various
Yes.
particle structures?
Yes, like what
This reminds me of a video from Unziker that I really liked about the defects in the lattice structure of space, which I think he pulled from like the 1800s or something. 1839, there it is.
it's like what you were talking about earlier, that particles are just oscillations in the ether. So this is what I think the ether is, and this is the oscillation
Talk
mode.
right into that microphone. You really have to
I'm a
be.
bit
You take it out of the holder and just like hold it right up to you when you talk. Otherwise, people can't hear you. And talk slower. It's
Okay.
There we go.
All right.
A proximity affected.
So I said when the thing rotates, it will emit a transverse wave, which will, on average, be spherically symmetrical around this structure, which becomes the electric charge of the electron, because that wave will interact with other particles like this. And if it's an electron, it'll constructively interfere with it and cause them to be repelled from each other. And if it's a positron, which is just exactly the same as this structure, only it's inverted in the lattice, and it will be, or the wave will interfere destructively with it and cause the electron and the positron to be pulled together.
How did you settle on this structure?
I settled on this structure because the tetrahedral lattice can also be looked on as 2 interpenetrating face-centered cubic lattices.
Okay.
That's nothing new that I've discovered. That's well known. So I seen there that you had 2 different components interacting oppositely with each other, and that gave me the idea that was the way to create positrons and electrons. Because I read a book a few years back by Ray Fleming. I think his friend is here. I must talk to you later. And he wrote a book called Goodbye Quarks, which gave me the idea that all the particles in the universe can be described by just 2 particles. And when I read about this tetrahedral lattice having these 2 interpenetrating lattices, I thought that's an idea for generating 2 particles. And then I reinterpreted the mu naught and epsilon naught by looking at Maxwell's equation for the speed of light, and its equivalent for the speed of, let's say, sound or a wave in any other medium is just the formula for the speed of a wave in a medium is just 1 over the square root of the bulk modulus divided by the density. So,
all right. I think I need to come by your poster, which I think is like half of this wall, written in 11-point font, and you will have to explain all of this to me when I have some visual aids. For right now, let's move on because we still have a lot of theorists, and I want to keep the show moving.
Okay,
but thank you so much, Michael Gunning.
Thank you.
Rehearsed at 54 seconds, but we'll see.
We've got a minute on the clock.
Yep.
All right, here we go. 1, 2, 3, go.
Quantum time dilation as a key to unifying QM and GR. In gravitational time dilation, all physical processes proceed faster at higher potential and slower at lower potential. In quantum mechanics, wave functions rotate their quantum phase faster at higher potential energies and slower at lower potential energies. These are not only qualitatively similar, but I claim they are different descriptions of the same physical effect. Identifying them gives a partial merger of QM and GR, but also shows that the theories directly contradict each other in at least two ways. To reconcile those contradictions, GR has to be extended to have time dilation-like effects for all potentials, not just gravity, and QM has to be modified so that the time evolution is exponential in energy, not linear. I conjecture that any logically consistent unified theory containing QM and GR as limiting cases must have both of these features. And the EM time dilation is testable using muons or charged pions. Yeah.
I bet.
By the way, Matt Fox is the next one on the mic.
Matt, you're up on deck. All right, Howard, I have a hard time with, is this a theory of everything?
No, this is a theory of something.
Okay.
Right? This is like, if the theory of everything is a skyscraper, this is the first floor.
Okay.
All right? And already we have to modify general relativity and modify quantum mechanics even to get the foundation of the building to sit flat, right? It's
And what is the thing that the first floor will explain?
well, it's surprising that a simple, stupid analysis of these really crude limits of the two theories already shows where they directly contradict each other. And you know, if you're going to merge them, you have to fix that, right? You can't have a theory that has internal logical contradictions. So I was able to fix both of them, but there's a very steep cost. The EM time dilation violates EM gauge invariance. So that has to go bye-bye.
I have a question. Do you have a set of multicolored shirts that have the same theory written on them for different days of the week?
Version 1 had one equation.
See, what
This is version 2. It has a lot of equations and one QR code.
Does the QR code link to more equations, Howard?
It leads to the paper that is on the back. Version 3, which is light blue and you've seen me wearing around, has about the same number of equations but 5 QR codes. And I have about a dozen of those mostly in XL and L, so if anybody wants them, 20 euros or make an offer.
Did you spend your career selling T-shirts? What did you do before you got into theoretical physics?
I was a electronics engineer for most of my career. I worked on the Berkeley RISC-1, and I was a co-designer of the main processor for the Sony PlayStation 2, and a bunch of other stuff that's less famous. So, and I'm kind of a hardware-software amphibian. And I did not intend to get into foundations of physics. I intended to get into quantum computing in the 2000s. And then I noticed this thing, and here I am. So,
can you talk right into that? Can you take the microphone out and talk right into it? No, just pull it out of the stand. No, just pull it. Yeah.
Curse here, yeah.
You know, one thing that I really like about this conference is that I keep seeing the same patterns coming back. And this reminds me a bit to what Chris Lehto was saying about this pattern coming back on different timescales. This is just a pattern coming back on different theories.
Well, I will note that I am the second person in this session to mention exponential quantum mechanics. We need to talk.
I got a question.
Yeah, go ahead.
What is time?
Oh.
It seems central to your theory.
Well, okay, so what's different in time in this theory compared to normal is...
Well, what's normal time? Like what clocks do?
Well, think of like special relativity. Okay, so you have different people can see time differently, but each...
Clocks, right?
Each clock sees its own proper time in a certain way, and everything in the same frame sees the same proper time evolution in special relativity. I'm saying that's not true because you can have time affected by electrical charge. So if you have like an electron and a positron in
I don't
the same
think you
Especially
frame,
these smartwatches.
I don't think you can use the word time in your definition of time.
Well, the clocks, they're what clocks do, right?
Did we agree on that?
I
Yeah.
keep, yeah,
Okay.
I
all
mean,
right.
basically here the particle's quantum phase revolution acts as its local clock in the Einstein sense.
Okay.
Well, that kind of makes sense,
Does
right?
it?
Like periodic motion. And so if you have like spin one half of the electron, the spin one half of the electron
Oh,
is
that's
the
the
clock.
clock.
Of that.
Okay.
Yeah, it's the clock.
All right. My
So
bad.
anything that changes the phase frequency is a time dilation. And if you disagree with that statement, you're saying that there is some other thing that can change phase frequencies that is not a time dilation, and I invite you to tell me
No,
what
I
that
like
is
that.
and
I
how
like
it works.
that. I like that. That's the least crazy definition of time dilation that I've ever heard, actually. Well, if you're talking about the motion of some oscillatory system that's changing, then
Okay, but
that's
as the
reasonable.
motion of the oscillatory system changes, there is another system that's outside of it that hasn't changed, right? Presumably, like there is, and like this is something that I've always wondered about, right? So we talk all the time about time dilation and relativity of time and the fact that it's really difficult to find like a single point where you measure from. But there are plenty of clocks in the universe that are all kind of going. And shouldn't you be able to take kind of like an average of the clocks to be able to say that like time has or has not dilated?
So in gravitational time dilation, the changes in speed of time are agreed upon by all observers, right? Because those things aren't moving next to each other. And so it's different from the special relativity time dilation, where if you're zooming by me, I think your clock is running slower than mine, and you think my clock is running slower than yours, right? So in the non-moving case,
Unless you're a photon.
well, yeah, but then you don't count time, right? So
I think that I got to put this back in the oven a little bit and think about it. But I do want to know, how often do people ask you about the equations on your shirt? Do you wear the shirts out when you go out into the world? And how often do people ask you about the equations?
sometimes, and at the APS meeting in the spring, everybody under 25 loved the shirt and the poster and was just like, oh yeah, I have a phone, I can get your paper, bing, 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 bing. It was all, and nobody over 25 stopped at my poster at all. You know, no professors, no other crackpots. And so it's like there's a generational thing.
Did you have enough QR codes on it? Did you have enough QR codes on it?
At that one, I only had this one, and then, but now I have 5 because there's 5 preprints. So
Excellent. All right, Howard, let's move on. Matt has just been frantically writing behind you. I'm very worried about what's about to happen to us. Thank you so much.
There's a bunch of numbers. We'll simplify it. We'll simplify it. Okay. There we go. We'll break it down. It's got me. Saw too many numbers.
All right, we got a minute on the clock.
Well, hold on, Vanya's.
Boxing him in.
Oh yeah, that's right.
You are corralled. All right, here we go. Ready?
Yes. And Taylor Trott, you're on deck.
On 3. You guys can say 1, 2, 3 with me. That'd be kind of fun. 1, 2, 3. Hit it.
All right. Within the realm of particle physics, there's something called the hierarchy problem, which typically relates to why the heck is the mass of the Higgs boson so much smaller than the Planck mass? On a previous episode of Paradigm Drift, we went over how we could computationally reduce the fine structure constant from all this jazz to elementary charge over the Planck charge squared. So taking that intuition, you take the mass of the Higgs, divide it by the Planck mass, square it, you get this number here, which shouldn't mean anything to most folks, but it's the first 3 significant digits in magnitude to h bar without dimensions. So, since algebra is awesome, to quote Thad, you can computationally reduce it, saying it's approximately
the magnitude of the elementary unit of action divided by the reference of action. Or to much simplify it, you can take the square root of h bar over joule seconds, aka the root of action, multiply it by the Planck mass, and you get within 4 megaelectron volts of the most recent CMS measurement.
Hey.
What is CMS?
It's the compact mu-node solar. It's one of the experiments at CERN. Between them and the ATLAS experiment, they were the ones that helped confirm that the Higgs boson, or something that we believe to be the Higgs boson, exists.
I have not yet managed. I have seen you present 3 times now, I think, and I still have not managed to wrap my head around it. So I will continue to try. Shiloh looks like he's got something to ask, though.
I actually just want to know more about you, Matthew.
Ask
So
away.
yeah, man. So how did you get into all of this? You seem you're everywhere. You seem to be talking to all of these really interesting people all the time, and you have your own podcast too, right?
Yeah. No, at the memes of destruction on YouTube and meme destruction on Twitter.
And you live at a physics monastery.
Yeah, about half my time. Long story short, should be easier to follow. I used to be in the realm of politics and everything. After I realized it didn't seem like people really wanted to solve problems, I came to science. And within the realm of science, I came across that at one point. Just random video there. I'm like, all right, bunch of claims. I have no idea. It's a dude on the internet. That was April 6th, 2021. The following day, April 7th, 2021, they came out with the muon G2 results from Fermilab. So since it was literally less than a day in my mind, I sent that a tweet. I asked, I don't know, but does this help your model at all? He responded, yes. I go back on to Fermilab's website, no idea what the numbers are, just look them up, look at the numbers that Thad had predicted the day before, and I'm like, he's within the error bars. What's going on here? So I reached out, I interviewed him several times, he invited me out to the monastery, went out there, and then I was blessed enough to be in a position to spend the past year or two of my life going out there and learning what Thad had to teach me. And after countless hours and thousands of dead ends on Wolfram Alpha, I'm pretty good at remembering the first couple of digits and exponential power. So I'm like, that's interesting. But last time it was only 3 significant digits. This time it's within 4. Technically, the change actually comes in the 6th significant digit that we haven't measured yet because we only have 5.
So now at this point, you're starting to predict significant digits as...
When that happened, I'm like, all right, now I need to finish that paper I started. Sorry.
You just grab it right
Oh.
out of the holder.
Yeah. So basically, after that point, I realized I started a paper, but with only about 3 significant digits. It's like but that ticks another significant digit, and if you divide it by this, you'll get like 1.0. It will go on for about 5 because the deviation comes where we haven't measured it yet. So it's a calculation, but more recently, I'm like, all right, and I'm going to read this. I'm like, so you have the elementary unit of action divided by the reference of action. And the main criticism I get is, oh, that would mean the joule second would be significant. Okay, now within the units of SI, the meter, it was like, well, is it like, take the North Pole by way of Paris to the equator and divide it by like 1,000,000. That's really arbitrary. The second was an earthly convenience because we have about 24 hours in the day. However, the relationship between these different bases and how they relate and their transforms, once they're in a coherent fashion, that kind of sounds like a tensor. Now, I'm not a mathematician, but I'm just interpreting this as the root.
You're not a mathematician?
Oh, no. I just pretend to be one on YouTube. But it seems as if perhaps the reason why the Higgs boson is so much less than the Planck mass is because it's scaled by the root of action.
Do you dream in numbers?
I dream about many things you guys probably wouldn't like to hear about, but
So, Matt, I wonder. We have probably people watching this YouTube video wondering how this will change their lives. So it doesn't have to be tomorrow, of course, but we know from Alexander's talks that in the end it's very important to look at formulas and wonder why. What do you think will happen with your formulas here and how it will change science and everything we do?
okay. As you said, short term, probably not a dang thing. Long term, if we have the ability to have higher precision, we should be able to, with that additional precision and knowledge, as Dr. Unzerker has highlighted, we should be able to engineer more cool things. And at the point where I had interviewed Thad and kind of seen a lot of stuff, it's like, if we have the ability to actually achieve universal replication by knowing how nature works the best we can, why shouldn't we be able to transform things so we can scan the best tomato in the world and we could have a true post-scarcity society where everybody could have that same wonderful tomato and maybe we stop, I don't know, dropping bombs on each other or anything. Personal opinion.
Sounds pretty cool.
I love it. Is there a clear line for you between the two? Like between being able to map this and then to actually build a technology that allows you to replicate the perfect tomato?
I mean, that's a hope and a dream, but if we were able to decode nature, as Dr. Unzerker and a number of folks here have highlighted, the better we understand nature, the more we can help use it, hopefully in a responsible way, to do more great things. I'm just basing that on history. So
the decoding of it gives us the ability to then mold it.
I mean, ultimately, that's the goal.
All right, well, let's see where it goes.
Cool. Thank you.
I love it, Matt. Thank you so much.
Thanks, Matt.
All right. Neal Creamer, you are on deck. Taylor Trott is up. You want to count them in?
Let's do it. 1, 2, 3, hit it.
Do some meteorites, namely the chondrites, like carbonaceous chondrites, such as the CR, CV, and H and LL chondrites, do they contain fossilized and petrified biological organisms and remains of those organisms? In particular, they might be permineralized or replaced by a magnesium silicate solution which contains iron and nickel. Why do I ask this question? And in particular, why do I disagree with why they were formed in an accretion disk and they may be instead from a solid liquid boundary on some moon or planet? In 2016, I started photographing the meteorites, every type of meteorite. I have over 250 thin sections, and I have a microscope which I create a grid of squares, and I focus stack each section of a thin section and stitch them together and post them online. And I had maybe 3 or 4 years into it, I thought I was seeing some strange things because I never knew that the sort of an organic theory in meteorites. And I had looked into has anyone else found this? And I found like in 1880, there was like Dr. Otto Hahn, and then in 1882, David F. Wineland posted a paper where he found 16 genre species. Randolph Kirkpatrick in 1916 came up with an idea that the meteorites were benthic deposits containing nummulites. In 1961, Klaus and Naj found organized elements in the carbonaceous chondrites. And in recent times, Dr. Chandra Wickramasinghe and Dr. Richard Hoover have found microfossils in the carbonaceous meteorites.
right, let's give him a hand. Yes, but not right that second. I'm sorry. This is why you can't give me the soundboard. That was excellent. You really buried the lead on the hundreds and hundreds of meteorite pictures that you've taken. How did you start taking photographs of meteorites?
I was looking for like a project that combined like photography. I was interested in photography. I was interested in astronomy. That's just one of my things I've always been passionate about. And I'm really good at computers, so I was like, let's take pictures of meteorites. And well, I guess I first looked at the Passamonte meteorite. It was a eucrite, and I just like was amazed by it and cross-polarized light. So I decided that's like a perfect like thing to take photographs of. And so I learned how to like. Well, at first I was taking pictures of them, and everything was like sort of blurry because I was using like some cheap microscope. And as time went on, I learned about focus stacking, and I started focus stacking my images and then combining them into one giant stitched image like a Google map where you can zoom in.
And so, how did you come up with your theory from these pictures?
I guess it was after maybe 3 or 4 years of just going through every meteorite I had and looking at the forms and structures in it, I started to see things that didn't look like they would be naturally made. And especially like in the carbonaceous meteorites, like I have the Moss meteorite, the Kainsaz meteorite. There's a few other carbonaceous ones from Northwest Africa. They had like strange structures and shapes in them. And I kind of like didn't know what I was looking at, so I started looking up like existing literature, like did anybody else see these things? And that's when I kind of learned about the other people. Like basically, I needed to stand in a long line of other people who had already come up with ideas about fossils and meteorites.
How do you fund your meteorite habit?
Yeah, I would say just by a full-time job, developer.
Developer by day, meteorite scanner by night.
Where are you from?
I currently live in Washington State, right outside Seattle.
Nice. How long you been there?
About 5 years.
Where'd you grow up?
I grew up in Texas, South Carolina, Maryland.
That's a lot of places to grow up. Army parents?
I guess sales
parents. Right on.
Did they sell meteorites?
No, it's construction sales.
How do your friends take your meteorite habit?
Are
you popular among your friends?
Well, I don't really tell people about it.
Nastya, stop bullying these people.
Just asking questions. Why don't you tell people about it? I would tell everybody about it if I had a collection of meteorites that I was taking photographs of and discovering, otherworldly microorganisms.
I find when I bring up meteorites, it sort of blank stares and they don't know what I'm talking about. And it's like trying to, I feel like there's a large educational gap in what meteorites are, where they come from, like that kind of thing in general, like what types are there. I find it's hard to find people who know about, like, and have a conversation about it.
What's the worst part of the accretion model for you?
I think like if you look like what's like in the chondrites, like they're some of them are like stony chondrites, and they're like you can hit them with a rod and they make like ding ding, and they make like a hard noise. Like it's like, how does that form in the vacuum of space? When you think about the vacuum and these little pieces coming together to form this solid object, it makes more sense to me that they were formed in a pressurized, like a benthic deposit, and they have been permineralized and replaced with other things. Although it's not all of them. For example, some carbonaceous chondrites that Dr. Hoover has been researching, they contain the CHNO elements already, so they're not actually permineralized or replaced. But I think the other chondrites might have been in maybe like a nickel iron solution or a magnesium silicate, because magnesium silicate is the predominant in the chondrites.
Did you bring any of your meteorites with you?
I don't have them with me, but they're all online at my website. Yeah.
Okay. I want to see your meteorites. Do you have any more questions, Patrick?
A lot, but not for now anymore.
Excellent. All right. Everybody find Taylor later. Let's go to Neal, and then I think we'll do Indranil to close, and then we're at time.
All right.
All right. Thank you so much, Taylor. Give him a hand. Give him a hand.
the stage.
Welcome to Paradigm Drift, Neal. Neal is, I think, the person who has been with us the absolute longest. So, Neal, welcome. I'm very excited to hear this.
We got a minute on the clock?
Let's count them in, everybody
and
together.
Indranil is on deck. All right, here we go. 1, 2, 3, hit it.
A different understanding of quantum mechanics might explain emerging complexity. There are no photons. Planck suggested that atoms continuously collect and store electromagnetic radiation at any of their resonant frequencies until a quantum of action has been reached. Only then, the atom can and must either promote one of its electrons to a higher energy state or emit the whole quantum of energy explosively and return to its initial state as though nothing happened. Alternatively, an excited atom may use the accumulated energy to enable a chemical reaction. If this occurs, the resulting molecule will usually have a different absorption spectrum with more modes of action, more modes of vibration than its progenitors. As the size of the molecule increases, so does the number of vibrational modes, and so does the amount of energy the molecule can harvest from ambient light. This might confer an advantage on larger molecules and favor increasing complexity.
All right.
Yeah. All right, so photons do not exist.
That's not my idea, that's Eric's. My idea is built on Eric Reiter's idea, which is his unquantum effect.
And so, can you tell me again the bones of the idea?
Of Eric's idea?
No, of the idea that you've built on top of the non-existence.
Well, maybe we should start with Eric's idea for people who don't know about it.
I'll just briefly recapitulate Eric's idea. So that's from Planck's 1917.
And then grab that microphone.
Yeah.
Just take it out of the holder. Talk right into it.
So Eric's idea is based on Planck's 1917 theory of heat emission, I think it's called. Basically, it's called a loading theory, and that is the idea that the oscillators or the atoms absorb light continuously up to a quantum of action, and then they have to do something, emit it explosively. So they emit a quantum, but they absorb continuously. And if that's the case, then atoms must be continuously absorbing whatever radiation in their environment is at one of their resonant frequencies. So I thought that must mean that there are atoms that are filling up all the time. Eric uses that explanation to account for why that particular atom in the detector goes off in the double slit experiment. So the hidden variable is not in the wave function, the hidden variable is in the detector. That's Eric's explanation.
And then you built on top of that.
Yeah, so I thought if atoms are continuously absorbing, maybe that's in the very nature of atoms that they harvest energy from the environment. And if that's happening, that's if you look out into space, for example, you see all these odd complexes of atoms. That might be what drives complexity. I mean, something drives complexity in the universe. If you look at
No heckling the theorists.
That will not be on the podcast. Just saying.
But yeah, we see, I mean, if you're anybody who's a biologist, I'm a biologist, you're a biologist, you see increasing complexity. There's always increasing complexity. And it was just, maybe that starts at the level of the atoms because of the way they interact with light.
Okay, so this is, and this is like a really vital question in biology, which is like, how do you get life? Right? Is because at some point you have atoms, and then on the other side of atoms you have life, and presumably there are places, like even if the process of life is eternal, there are still places where life kind of
occurs.
It starts. Is that fair to say? Like
Don't ask me.
I think it is. Like I think that it is fair to say that.
I was thinking life is very often breathing, and I feel breathing.
It's also breathing, technically.
Breathing and breeding, actually.
we can go to the second one later. But so the one with the TH. So I can feel a rhythm in your theory. Yeah, you're absorbing energy and it explodes at some point. Does this define time, you think, or is it defining a certain quantum rhythm? No, unquantum rhythm.
There's an interesting thing, actually. I did say, yeah, in that an atom might absorb energy and then just explosively emit it, the whole quantum. And then there's no history there. Nothing's happened. That's physics. It's like the symmetry of physics. Nothing has happened. But if it promotes an electron and there's a reaction, then you've got chemistry, and then you've got history. And this is like goes towards Prigogine and the arrow of time. So you could have this symmetrical process where the atom just emits and nothing happens. But as soon as chemistry happens, history starts to happen.
That's the breathing.
That's a T-shirt right there. History starts with chemistry.
There you go. There you go.
That's the breathing with a D, yeah? We have it.
We have it. We've come full circle.
I think we're getting mighty close to the end of this thing. If we want
We
to,
are.
did you have another question for Neal?
No, but I do think that you should talk to John Mullins because
Definitely.
he's he and I spent all of last night talking about something that's like one step above this, and this slots very neatly into the foundations of it.
Yeah, just one other thing, that absorbing energy means things can do more. That's the advantage of absorbing more energy. It means they can do more.
I really like that.
Yeah.
That's very cool. Thank you so much, Neal. All right, let's give it up to the last theorist of the night, Indranil. Woo! Indranil, grab that microphone before you start. So as you present your theory, take it out of the holder, and then.
Is it working this way?
Yeah, but it would be better if you could hold it. So if you just pulled it out, there you go. All right, let's do it. Let's count them in all together.
1, 2, 3, hit it!
One of the biggest mysteries in cosmology at the moment is the Hubble tension, the observation that redshift rises with distance more steeply than expected in the standard cosmological paradigm known as lambda CDM. If you calibrate its free parameters using the observed anisotropies in the cosmic microwave background radiation and its temperature. So my idea is that this anomaly is caused by our location within a large void or underdensity. That's approximately 20% less dense than average, out to 300 megaparsec or 1 billion light years. And the extra sort of outward gravitational push or anti-gravitational effect of this underdensity creates outward motion beyond that which arises from cosmic expansion. And this leads to the appearance of a faster local expansion rate. So I've been working on that, and we've recently confirmed some key predictions of this hypothesis using measurements of baryonic acoustic oscillations collected over the last 20 years, especially the DESI-DR2. So check out MNRAS 540, 545 if you want to learn more about this.
All right.
Indranil, why are there voids?
Well, there was a small amount of structure in the universe initially over dense and underdense regions, and the underdense regions they gradually become more and more underdense because matter flows out of voids and into the overdensities. So it's just sort of random initial fluctuations that grow over time.
Do you think the underdensity is relevant to the fact that life is occurring here?
There may be some anthropic selection effects because in an underdense region, there'll be less likely for galaxies to sort of collide with each other. And more generally, the proportion of spiral galaxies should be higher. And these provide a much better environment for life to start because of stars not intersecting each other's orbits as much as they would in an elliptical galaxy. So there may be some relation.
I want to know more about you, Indranil.
Okay.
You seem like the type of guy who was doing physics before you could walk. What's your journey like to this point?
Okay, so I've wanted to do astrophysics since I was about 5, so that's reasonably accurate. The main thing I wanted to find out is if the laws of physics and chemistry that sort of work on the Earth, that we can verify, if the same sort of laws and principles apply to other distant celestial objects. So, for example, I was seeing Mars through a telescope, and you can see like polar caps on there, and they are similar to the ones on Earth, but they're made of carbon dioxide rather than water. But nonetheless, most of the principles that we've learned on the Earth do apply to Mars. But then you can ask the same question further away. And for example, we know how, with Kepler's laws, how planets orbit around the sun in the solar system, but that doesn't work for a galaxy. So at some point, new phenomena come in which have no terrestrial analog, and astronomy provides the only real way to learn about them. So I've been a researcher for the past 10 years.
Do you own a telescope?
Not at the moment, no.
Oh, we're gonna have to we need a Kickstarter to get this guy a telescope.
Did you spend a lot of time staring through telescopes when you were younger?
Some, yes. We looked at Mars and also at Saturn and its rings when they were open.
How did you become a theoretical cosmologist as opposed to observational? Was it something that just drove you more towards theories?
Well, I've just always sort of enjoyed the mathematical aspects to it. Once I could handle equations and coding them, I just saw myself more as the person who sort of builds models or develops and quantifies other people's models in more detail and then relies on others' observations to compare them with. So it's just kind of naturally the aspect that I sort of enjoy more.
Do you think that with the complexity of models that are currently being used in astrophysics and the size of data sets and the processing that happens to them before they get to the researchers and the theoreticians, do you think that there's any place for systematic problems to crop up?
I mean, that happens all the time.
Do you think that they are easy to spot and eradicate?
Well, it depends on how big of a systematic effect it is. Of course, systematic effects such as changing some arbitrary model assumptions or human choices regarding where to place quality cuts. Like if these are smaller than the official uncertainties, that doesn't really matter. Ones which are sort of many times larger than the uncertainty, I think they typically do get spotted simply because of the large size of the teams. But sometimes I worry that this push to do blind analyses, which is motivated by a desire to avoid human biases, that can actually, in particularly cutting edge and challenging areas of astrophysics, it can actually make it harder to spot systematic errors because people aren't allowed to look at the actual data until very late. They have to look at some kind of adjusted version of the data, which may hide some of the problems. So there is a bit of a conflict that is often not appreciated between the desire to blind researchers to the result and how accurately they can actually do the work.
So yeah, I remember from the podcast that Nastya was calling you like a paradigm repairer. And I think we saw that here in the conference quite a bit, together with your also keen eye on watching the anomalies and seeing what you can repair there. I wonder, what is it that drives you? Is there an ultimate goal that you have in your career that you would say, then if I reach this goal, I will feel accomplished? Or is it that you more feel like playing around and building things out of voids?
So, I mean, for a long time, for about 10 years, I worked on the Mond-Milgram dynamics hypothesis. And then I thought a natural sort of culmination would be sort of confirming Mond using the wide binary test of gravity. But as some of you know, this went the other way. It actually falsified MOND. No, at the moment, I would say my goal is to understand what is the origin of this Hubble tension. If that can be solved, that would be my sort of culmination, if you will.
Do you think you're close to solving it?
Well, I have an idea on how to solve it. But it's a question of how close we think we are to confirming that, and I think it's not too far off. Perhaps another decade or so should be enough to at least. I was actually the director at my institute actually asked me to do a calculation of a futuristic sort of experiment that would be able to get decisive results using the so-called redshift drift experiment, which is where you simply wait for the redshift of an astronomical object to change over time. I think it's clear that the Hubble tension shouldn't be a problem 50 years from now. It'll get solved within that time frame somehow or other.
I don't know if that's optimistic or realistic or pessimistic. I have a hard time gauging.
But it was good because it sets an upper limit, I think, on how long the problem might remain.
So if it's still here 50 years from now, I'm coming to find you, Indranil.
Well, it shouldn't be here 50 years from now.
I'm going to hold you to that. I think that, so because we are running this portion of the event, we are actually going to end exactly on time. It is 4:30 on the dot. I want to give a big round of applause to all of our contestants. And to the Baryonic Acoustic Oscillators.